Until now, I've made videos about quite a diverse range of topics, sure, let's call it that. And I think that it's time to step back into the area that I know the most about. That's computer science. And before you click off of this video, just let me say that I'm not going to get too far into it, so you should probably be able to enjoy this video even if you don't know a thing about computers. Seriously, sit down and shut up, it'll be fine. You might even learn a life lesson or two. So there's a website that I use sometimes called Caddis that has a lot of programming problems, and the one that I want to talk about today is this. You're given a big sheet of paper with outlines of a lot of boxes on it. None of the boxes are rotated, by the way, and you're not allowed to move them. The boxes are described by their top left point and a width and a height. Every once in a while the boxes will overlap, and you want to find the area of the group of boxes which do not overlap that takes up as much of the paper as possible. It's important to note that you don't actually have to keep track of the boxes that are in that group, just how much area that they take up. In order to make sure that there's a bit of a challenge, you also have to worry about how long it takes for the program to run. In this case, we have to make sure that it can handle 500 test cases in less than 2 seconds. So it's gotta be a pretty good solution. Caddis also pinky promises that we're not gonna have to worry about more than 20 boxes per case, though a good solution would probably work decently quick with even way more. So it's pretty obvious that there are a lot of different groups that we're gonna have to look through. For every single box, we've got a choice of either including it or not, so there are 2 to the number of boxes different answers that we have to check. So we'd have to check if there was any overlap and calculate the area for up to 2 to the 20 cases, which is well over 1 million. Just simply doing that is going to be way too slow. We're going to have to think about it a little bit. So obviously we don't have to actually check if there's an overlap every single time. We can just check each pair ahead of time, and when we're considering a scenario, if any of the pairs inside of it overlap, then the case is invalid. Even better than that, we can also divide the boxes into subgroups which don't actually interact with each other. And if the 2 groups don't interact, then we only have to calculate the maximum area of one subgroup at a time, and then just add them all up. Now it seems to me that 2 boxes overlap when one of their corners is inside each other, so let's just code it all up and... it's wrong? Wait. So imagine that we had 2 boxes set up like this, where they're both so big in one direction that they overshoot each other. So if we check all of the points on this line, as well as the corners, then we should be able to catch that. Alright, that made sure that all the answers were correct, but we're still way too slow, and now that I think of it, if we're considering a scenario that's just a more complicated version of one that we already know has an overlap, then we don't actually have to check anything, because it's not going to be valid. So let's just test it out, and it's still too slow. Now, at this point, I decided to try everything. And this is a little bit of hindsight, but to really understand how we can make the solution work, we need to understand what's actually going on inside the computer. So the obvious solution, that is the wrong one, is just to construct a giant array of numbers which represents the areas for each of the 2 to the 20 cases, with cases with overlaps being represented as a negative number or 0, however you want to do it. But 2 to the 20 is over 1 million, and changing every single number inside of that array means well over 1 million operations on it, and we want all of them to finish within a tiny fraction of a second. But because of the way that arrays work in a computer, if you've just accessed, say, the second value, then accessing the third value will be a lot quicker than accessing the 10,000th value. But with our problem, there isn't really a way to number all the scenarios in such a way that a specific scenario is going to be right next to the slightly simplified version of that scenario. Really, if you're gonna use one, you're gonna have to jump around the array a lot. So any solution that doesn't use an array is probably gonna be faster. But when I was originally trying to solve this problem, instead of doing that, I optimized the shit out of the for loop checking every single case. But no matter how I was able to speed it up, I was only able to get the trivial cases to be fast, like checking a scenario where a bunch of boxes that totally don't interact. The hard cases, the ones that actually took a lot of time to calculate, didn't budge. And really, everything about the obvious way to go about this problem makes situations that are simple easy, but don't really make bad situations faster at all. I'll admit, at this point I was totally stumped, and I realized that a working solution wasn't just a few edits away, it was going to take rethinking the entire problem. So I looked up a solution. And I think it actually teaches a lot about optimization and, more generally, how to approach a problem in life. So, what if we didn't calculate anything about the cases which we already know aren't the maximum? Instead of checking every single possible combination of the boxes, the solution uses a technique called recursion, basically a function that either has a value or calculates a value by calling itself again to check only the boxes which don't have overlaps. So first you gotta number the boxes. Then we want to keep track of the boxes that we're considering already in the result, and the box that we're considering adding to that result. If the box that we're thinking about adding conflicts with anything already in, then we just return the best result without it. If it doesn't conflict, then we return whichever is the maximum of the best with it, plus its area, or the best without it. If we ever get to the point where we're considering a box that doesn't actually exist, you can just return 0, because the lack of boxes is no area. And the recursion at that point will start to unwrap itself. When you explain it like that, it sounds extremely basic, and it really is. The best part is that because of the way that recursion works, the max including box 1 will wait on max including box 2, and so on. So a maximum of 20 numbers have to be kept in memory at one time. That's about 50,000 times fewer maxima that we're keeping track of at any one time. And that only gets better if we do situations with over 20 boxes. Importantly, this means that in really bad cases, like the one where all of the boxes overlap, are actually handled really quickly because we realize that after adding the first one, adding another one will always cause an overlap, and the recursion can exit at that point. I ran a scenario where all of the boxes overlap, and it finished in less than a millisecond. If 1 millisecond is our worst case, and it probably isn't, but whatever, we might be able to handle as many as 2,000 test cases. In fact, it turns out to be so quick that the whole splitting the problem into groups that don't interact idea isn't actually an improvement at all. The general technique here is called backtracking, where you try and get as far as possible until you know that you can't go any further, and you revert back to an old state, like going through a maze. It's a whole thing in programming, and it turns out to be extremely powerful in dozens of similar problems. There's also another slight difference with the solution that I found. Again, all credit to this guy, link in the description. But remember when we did that weird shit with checking if the boxes overlapped? Well, it turns out that I'm incredibly stupid, and you can actually just use the width and the height, which I assumed was given to you to make it slightly harder to find the corners' locations. For example, if 2 boxes' top left corners are within the width and height of one another, then they're necessarily overlapping. The solution that I thought I had was also incorrect in a few cases, like where the boxes overlap over a single unit, and their corners are outside or on each other's edges, not technically inside. There's still an overlap, but because I was only checking on the grid lines, it wouldn't detect it. So, what are the lessons we can learn from this problem? And my being confused by what is honestly not that bad? Well, first and foremost, think about why you're told what you are. Width and height were how your program should think about boxes because that's ultimately the key to doing the first step of the problem. If something about the problem you're facing seems to be a bit roundabout and nonsensical, but you think you know a way to smartly reframe it, consider if you're actually being an idiot and think about the advantages of the way that seems dumb to you. As far as the recursive solution being superior to the iterative method, always consider what you're going to be spending the most time and effort on, and actively try to make that easier instead of working on things that are already easy. You might be able to change your old worst case scenario into something that you can handle with ease.